Hi, my name is Ramamurthy Bhagavatula. I'm a staff member at MIT Lincoln Laboratory, and I've had the pleasure of leading the Beaver Works Summer Institute piPACT independent project this summer. The project provides participants an opportunity to explore and contribute to Bluetooth-based COVID-19 contact tracing efforts, such as the Private Automated Contact Tracing, or PACT program. Each participant is responsible for choosing an aspect of this application to explore in depth and evaluate. Working with Raspberry Pis, participants conduct data collection experiments, perform analysis, develop algorithms, and make technical conclusions. Participants' efforts contribute to the larger body of knowledge that is critical to making such contact tracing technology both feasible and effective. Welcome everybody to the piPACT Independent Project webinar. I hope everyone's been enjoying the Beaver Works Summer Institute final event. I know the courses have been doing some really great work, and I hope you've been able to enjoy all that. So before we get started, I'd like to give everyone a little bit more background on exactly what piPACT is attempting to do and provide an opportunity to students with. And that begins with understanding what exactly contact tracing consists of, what role it's meant to play in mitigating epidemics like the one that we're currently experiencing of COVID-19. So a short little YouTube video we'd like to play for everyone to get that sense of what COVID tracing or what contact tracing is all about. And this is courtesy of UT Health Austin. So that brief video basically showed us that contact tracing is the process by which, again, that video explains what contact tracing is, which is the process by which medical professionals trace the route of transmission starting from a positively diagnosed patient. In this way, they aim to break the chain of transmission by notifying and taking hopefully preventative preventative measures from preventive measures against further transmissions. So as that video actually demonstrates, currently that contact tracing process is manually done. It's with actual humans in the loop, with trained professionals doing that query of positively diagnosed patients about who they've been in contact with, where they've been, so on and so forth. And as you might expect, as the numbers of positive cases go up, the task of doing contact tracing for all those individuals becomes prohibitive, both in terms of time and resources. So naturally, when you hear the words prohibitive, time, and resources, thought quickly goes to how can we bring technology to play to lessen that burden. And one way that is being explored with regards to contact tracing is by applying Bluetooth technology to automate contact tracing. And so there are many efforts going on worldwide. I'm sure many of you have heard of them. But one in particular that's going on more locally here in the United States is called the PACT program. And I have another video here that I'd like to play that explains exactly what PACT is doing and helps explain how Bluetooth technology can play a role in facilitating contact tracing. So this video explains PACT.
When a patient is diagnosed with an infectious disease like COVID-19, an important step in slowing the transmission of the disease is contact tracing. Contact tracing seeks to identify the people who have had close contact with the infected individual and who therefore may be infected themselves. This targeted strategy reduces the need for stay-at-home periods. However, manual contact tracing is subject to a person's ability to recall everyone they have come in contact with over a 2-week period. There is need for an automated, privacy-preserving contact tracing system. MIT is developing one such system. Cell phones are constantly advertising their presence using Bluetooth. These advertisements, which we call chirps, can be anonymous and contain no location data or personally identifiable information. Every phone stores a list of all the chirps that it has sent and all the chirps it has overheard from nearby phones within arm's reach. The MIT system utilizes these lists to enable contact tracing for people diagnosed with COVID-19. This system not only identifies contacts, it also estimates the distance between individuals, as well as the amount of time they spent in close proximity to each other. When a person is diagnosed with COVID-19, public health professionals would coordinate with the patient to upload the list of chirps sent out by their phone to a public database. Meanwhile, people who have not been diagnosed can have their phones do a daily scan of the public database to see if their phones have overheard any of the chirps used by people later diagnosed with COVID-19. This indicates that they were in close, prolonged contact with that anonymous individual. Depending on the circumstances of contact, they may be referred to the public health authorities, who may recommend varying courses of action, including symptom watch, testing, and self-quarantine.
Contact tracing is a critical tool in our fight against infectious diseases, and PACT, or the Bluetooth-based contact tracing approach, is a specific tool or specific instantiation of contact tracing, which will hopefully allow us to scale to the scope of the current crisis. So piPACT has given Beaver Works Summer Institute participants an opportunity to investigate this technology and contribute to achieving that solution. Over the course of the program, we actually had close to 180 participants, of which a little over 130 successfully completed the projects. They will all receive certificates of completion in recognition of their efforts, and in special recognition of their efforts of a subset of folks. 10 individuals have been recognized for exceptionally impactful, exceptionally disciplined, and exceptionally rigorous work, whose names I will now read out in alphabetical order. So Alex Gerber, Nadine Han, Audrey Lee, Jackson Oliver, Joseph Rosenfeld, Michael Rebalkin, Maxine Shi, or I apologize, Maxine Shi, Rishi Sinha, David Wang, and Alice Wu. And at one more level of special recognition, 4 of these 10 have been selected to give presentations on their work so they can share with you, the exact scope of their efforts. First up is Jackson Oliver, whose work is titled, Using Signal Filtering to Reduce RSSI Variability and Increase Classifier Accuracy. And so at this point, I'd like to ask Jackson to share his presentation along with turning on his video if he so deems. Jackson, the floor is yours.
Okay, hi everyone. My name is Audrey Lee. I'm from Mira Costa High School in California. And today I'll be talking about my piPACT project, which explored the effects of different meteorological factors on RSSI. So as most of you probably know already, the goal of PACT is to use Bluetooth devices, the RSSI values in our case, to determine when two people are too close to each other for too long. And hopefully this contact tracing system will help us slow down and stop the spread of COVID-19. However, I'm sure you can all come up with a lot of questions about the feasibility of this system. And the question that I asked was, how are different meteorological conditions going to affect the performance of Bluetooth in this system? Now, why did I pick this question to focus on? Well, when implemented, the PACT system is going to be used across the United States, and depending on how long COVID-19 lasts, likely throughout the year. The system will have to endure a variety of weather conditions, but we don't know yet if RSSI readings on, say, a hot and humid day are going to be consistent with readings on, say, a cold and dry day. Therefore, my hypothesis was that meteorological conditions have an effect on RSSI. And I wanted my experiment to cover as many components of meteorological conditions as possible, so I stuck to observing and establishing any effects rather than developing a system to account for those effects. As for which components I focused on, I first compiled a list of the potential components and picked the ones that I thought would be the most feasible for me to simulate at home. In the end, the 4 factors I chose were temperature, humidity, atmospheric pressure, and wind speed. So let's talk about how I actually carried out my experiments. One important thing I did was manipulate one variable at a time while keeping the other 3 constant to determine the effect of each factor without interference from the other factors. In the end, I used 2 different setups. The first one was for temperature and humidity. Basically, this is a long tube made from an insulating material, and it's held in a box-like shape by the 2 cardboard boxes on either end. I used this BME 280 sensor to record the temperature, pressure, and humidity inside of the box. For temperature, I used dry ice to lower the temperature down to -8 degrees Celsius and took scans while the temperature slowly rose back up. And I used a hairdryer to raise the temperature up to 40 degrees Celsius and took scans as the temperature fell. And I did a similar process for humidity. The humidity was lowered down to 28% using some moisture absorbing packets that were placed inside of the box, and the humidity was raised up to 85% just by spraying water into the box. For both of these experiments, I did 3 trials. The second setup was used for my pressure and wind speed experiments. For pressure, I put caps on the ends of a long ABS pipe, as you can see in the top image, and I attached a vacuum pump. I used the vacuum pump to lower the pressure down to about 63,000 pascals and took scans as the pressure came back up to about 100,800 pascals. I did 5 trials for this experiment. For wind speed, I had to do it a little bit differently because my fan only worked at discrete speeds, so I couldn't take continuous readings like I did with the other experiments. Instead, I took readings for 120 seconds at a time at wind speeds every 5 kilometers per hour, from 20 kilometers per hour to 60 kilometers per hour. I did 3 trials for this experiment. So to analyze all of the data that I had collected, first I aggregated all of the data from all of the trials in each experiment and created scatter plots. Because I had both pies acting as both a scanner and an advertiser, I ended up with 8 scatter plots from the 4 experiments with the 2 pies. I used the pandas library to read the data, matplotlib to create the scatter plots, and numpy and scipy to compute the line of best fit and the r-squared value. So let's go through the results of each experiment. For each of these scatter plots, I overlaid the data from the 2 pies on top of each other, which is why you see the 2 red lines of best fit. So for temperature, the plots indicate an inverse relationship. The regression coefficient of the 2 lines is about -0.27. The r-squared values were fairly significant, being 0.23 and 0.19 respectively, which supported the existence of a negative correlation. For humidity, the plots didn't indicate a relationship at all, judging by both the regression coefficients and the r-squared values being almost 0. However, something to note in my humidity experiment is that the 2 pies had different results. As you can see, the top red line has a steeper slope than the bottom line. This discrepancy could be a result of the natural variation of RSSI readings, a consequence of one of my initial assumptions, or it could be something that should be explored in further experiments. For pressure, the plots indicated a slight direct relationship. The line of best fit had a positive regression coefficient of 0.0001, and the r-squared values were the most significant at 0.26 and 0.22, which supported the claim that a direct relationship existed between pressure and RSSI. And finally, for wind speed, You'll see that the plot looks a little bit different since the scans were taken at discrete intervals. Therefore, I was able to plot the average RSSI along with the scatter plot. However, I did not find any relationship between wind speed and RSSI, which was again supported by a regression coefficient and R-squared value of almost 0. But there's, again, something important to note with the wind speed data, which is that the variation in average RSSI values seems to increase as wind speed increases. You can see that the variation from 50 kilometers per hour to 60 kilometers per hour is definitely greater than from 30 kilometers per hour to 40 kilometers per hour. Again, this may be the result of the natural variation of RSSI, and it may not even be significant because all of these values ended up fitting within a margin of error of 0.05%. So based on those results, let's talk about my conclusions. First, here's a reminder of the results and of my hypothesis. Based on those results, I determined that my hypothesis had been false. And the reasoning for that is that of the 4 factors that I tested, 2 did not have an effect and 1 barely had an effect. So while the meteorological conditions in general don't have an effect on RSSI, my experiment has shown that it would be more accurate to specify that temperature has an effect on RSSI. For some noteworthy conclusions and general lessons, the first is that when trying to account for variations in meteorological conditions when designing a PACT system, variations in temperature should be prioritized. The results found that RSSI decreased by 1 for every 3.5 degrees Celsius increase in temperature. Because the temperatures in, say, the winter and the summer can differ by more than 35 degrees Celsius, the RSSI would therefore differ by more than 10. Second, I concluded that the effects of pressure did not have to be prioritized as heavily as those of temperature, but they should still be prioritized over wind speed and humidity. The results found that RSSI decreased by about 5 over a change in barometric pressure of almost 40,000 pascals, or a change in altitude of more than 4,000 meters. And since most of the United States is at an elevation of 4,000 meters or less, the RSSI would be within a margin of error of just plus minus 2.5, which is not as drastic as the effects of temperature, but still more noticeable than the effects of humidity or wind speed, which is none. And so what are the next steps? Well, in my report, I explicitly mentioned 3 potential next steps. The first is to look at the effects of more meteorological conditions, of more factors. As I mentioned earlier, I had to rule out some factors that just weren't feasible for me to adequately simulate at home. So I thought that in order to fully know the effects of meteorological conditions, experiments should be done with the factors that I left out, like precipitation, solar radiation, or cloud cover. Number 2 is to get better environmental readings. While the BME 280 sensor that I used was inexpensive and fairly easy to use, it certainly wasn't a top-notch sensor. And since I only had one, I had to assume that the readings from that one sensor were consistent throughout my entire experiment space. So in order to improve the accuracy of these readings, I said 2 things I could do were to first use a better environmental sensor than the BME 280, and second, to use multiple sensors and space them out along the 1.8 meters so that the values could be averaged and therefore more representative of the whole space. And finally, use different devices. In the end, the PACT system is going to be implemented on actual smartphones, not Raspberry Pis, because people don't usually carry around Raspberry Pis with them. I used Raspberry Pis because those were provided to me for this project, but the experiment should still be repeated using various smartphones and the environmental sensing capabilities of those smartphones, or maybe even the local weather reports that the smartphones have access to, because that would better represent the final iteration of PACT. And also, this would confirm whether my findings are unique to the Raspberry Pis that I used, or whether they're consistent across Bluetooth devices. And finally, these are the references that I used for my report. And thank you all so much for listening. I believe now is the time for questions.
Thank you, Audrey. Yeah, so I apologize, but I failed to mention, so on the main webinar page, there's a Q&A entry box that you're welcome to submit questions for Audrey or for any of the subsequent presenters. But I do have a question to get us started. So Audrey, your work obviously demonstrates a fair amount of physical hardware and data analysis. What aspect do you think was the most challenging to realize, and how might you improve it going forward?
Well, I would say that the most challenging aspect was really just figuring out how to get started. Once I had the idea for studying the effects of different meteorological conditions, my main challenge was just really figuring out how to get started with simulating those at home. I don't have access to any sort of weather lab or anything. So it was a challenge to use household materials or materials that I could buy at like a local hardware store to create an accurate simulation of each factor.
So let me ask one more question, and then we'll see if the audience has. And I think you already alluded to this, right? So obviously, one implication of your work is that by taking into account the effects of the meteorological factors, we can make such contact tracing approaches more effective, more reliable. And smartphones don't necessarily come with instrumentation that might, that you can basically glue on. What sensors do you think we might want to consider leveraging, or data sources leveraging, in order to exercise, the conclusions you've made?
Well, I don't know that we would necessarily be using sensors because it would be difficult to implement those sensors on all of the smartphones that are already in circulation, since that would be where PACT would be finally implemented, which is why I mentioned potentially gaining access to local weather data from local weather stations and taking any information on temperature, humidity, and atmospheric pressure from their measurements.
All right, excellent. So I think we don't have any. We have a lot of positive comments, by the way, Audrey, from the Q&A. A lot of people very much think highly of your work, which is excellent. No direct questions. So just in the interest of time, we will first thank you, Audrey, for your work, your presentation, and for the very clear explanation of everything you've done. Hope you continue to do good work in this at this level, wherever your path takes you. And thank you for participating in piPACT. So with that, we will transition or get set up for the next presenter, who will be Jackson Oliver, who we've addressed his technical difficulties, it appears. So with that said, Audrey, if you okay, good. Yep. So once again, Jackson's work is titled Using Signal Filtering to Reduce RSSI Variability and Increase Classifier Accuracy. And so, Jackson, if you're ready, please go ahead and take the screen and the audio. All right, Jackson, floor is yours.
All right, Jackson Oliver. I'm from California, small town called Angels Camp. It's pretty nice. My work was on using signal filters to reduce RSSI variability, and in doing so, hopefully I could increase classifier accuracy for the purpose of piPACT projects, or really Bluetooth contact tracing in general. First slide would be nice, please. Thank you. At its most basic level, contact tracing depends, at least Bluetooth-based contact tracing depends on the relationship between RSSI and distance. However, the received signal strengths are often incredibly variable, which can make it difficult to distinguish between distances while still accounting for other environmental factors. As shown in the graph, they overlap greatly, which can make it very difficult to determine which distance exactly an RSSI value corresponds to. My work concerned the use of signal filters commonly used in other received signal techniques to improve the value of the signal received and to make it easier to classify these signals as a distance. A signal filter is commonly designed to remove or suppress some aspect of a signal. Some of the filters here are applied in a broader context they may not necessarily be meant for. The RSSI values are received constantly, and a signal is more commonly received in a short burst. Next slide, please. The experiments here were conducted using the provided materials, the Raspberry Pis and reference code, without any changes of my own. They worked fantastically, and I simply put them in varied situations. This was in an attempt to gather test data, RSSI data that could, in some aspect, represent what might be seen in practical application. Although I had many physical restraints that prevented me from doing multiple environments like I would have desired. As you can see in the table in the bottom left, I only had 4 general environments. One was plein air, one had a body in between the 2 Raspberry Pis, one was set in the outdoors on a patio, and one was in motion to determine the effects of filters and the use of classifiers on moving devices. It should be noted that these tests were all done in order to evaluate the use of filters and were not done with the intent of determining the effects of environmental factors on RSSI values. Next slide, please. And I'm going too fast. The analysis was the most important part of this project. It was done by applying all the signal filters to the collected RSSI values in each environment, and then generating receiver operating characteristic curves from that data. These receiver operating characteristic curves are a metric for determining a classifier's accuracy in determining which of a binary value or which binary thing it classifies it as. The filters applied were simple moving averages, exponentially weighted moving averages, median filters, Weiner filters, and Savitsky-Golov filters. Each of these filters operates by performing some function on a moving subset of the data, referred to as a window. The functions are shown in the slide. A simple moving average is what you would expect. It takes an average of the subset. Weighted moving averages do the same thing, but it weights the data exponentially biased towards the more recent values. Median filters take the median of the data in the window. A Weiner filter calculates new values based on local mean and variance estimates, and a Savitsky-Golov filter fits low-degree polynomials to the data in the subset. It then uses those polynomials to estimate where data might be and to generate a smoother curve. Thank you. After examining the effects of the filters, it was concluded that the hypothesis was correct and that the use of filters could improve the ability of a classifier. However, it could only improve the ability of a classifier by a rather marginal amount, on average around 0.03 or 3.4% improvement. However, in a few certain cases, for example, in a body test with one person in between, the use of filters could drastically improve how a classifier determined distance, and it could see as much as up to 20% improvement. This was exponentially better than all the other tests, and it was definitely worth noting. However, a few major faults can be found in using these filters, especially if they were to be applied in real-time application. These use the windows, which means that they collect data from a certain subset of RSSI values, and that means that they follow a certain time period as well. Within this time period, the devices could have easily changed the distance between them, which would skew the values and make them less accurate. In addition, none of these filters were applied in real time as I would have liked. They were instead applied after collecting the data. This means that they weren't, ready for practical application yet, though that could always be addressed later. It's my belief that this project should be interpreted as something like a proof of concept. I believe that the use of these filters is possible and that they could provide serious benefits to any Bluetooth-based contact tracing system. However, the work I've done simply isn't substantial enough to completely use in any Bluetooth contact tracing system, and it would definitely require more research and more experimentation to be practical. This data only examined the performance of 5 filters. A larger selection of filters and a larger selection of environments could definitely improve our knowledge of how filters work and how they would affect classifier accuracy. The large time intervals limited the size of the filter windows, as if I made it too long, the time period would be too great and the distance between the devices would be unknown. But decreasing the time intervals would also make the window smaller and decrease the ability of any filter to actively work upon the data. As thus, if the time intervals between RSSI values were decreased, it would very much improve the ability of a classifier and of a filter, allowing it to collect more data in a shorter period of time, improving the accuracy on both fronts. In addition, if these were to be used, it would be nice to be able to filter the data in close to real time, but that would mean that it could not affect or use any data from the future, meaning all the filters would need to be causal. However, this could likely be easily implemented with a few adjustments to the code. The entire too long aspect of the too close, too long of the Bluetooth contact tracing system wasn't addressed in this project, though I believe it could be rather simply addressed. However, it would definitely need to be investigated in order for any of this to be put to practical use in any sort of environment. It's also my belief that these systems, these filters, could work far better in a confined environment where you can define some of the environmental characteristics, and by doing so, you could optimize the filters to work in that specific environment. While this would severely limit the application of contact tracing, it could be done in certain hotspots like hospitals or schools where people are commonly at risk and nearby each other. It's my belief that the use of these filters could seriously benefit any Bluetooth-based contact tracing system, particularly PACT, but I would like for there to be more research before they were used.
Thank you, Jackson. That was an excellent presentation. So let me just check the Q&A. Do you believe, so answer this to the best of your ability, do you believe that other order statistic filters, for example, maximum RSSI or M of N detectors may have performed better?
Yeah, I certainly do, and I would have liked to have tested a lot more of them, as I stated. A lot of them were simply beyond my own personal ability to code into my design. I think there were a lot of filters, M of N filters, maximum filters, that could have definitely benefited far more.
All
I
right.
certainly would have liked to have studied those.
Here's a general question for you. What did you like the most about Beaver Works Summer Institute, whether it be piPACT or otherwise?
For this one, I sincerely enjoyed the research opportunity. I'd never done a research project before, and researching on its own was a fantastic feeling. Tackling a problem nobody had solved yet gave me a thrill unlike anything else I'd experienced in school. In addition, it felt nice knowing that I was doing something that could possibly benefit with the COVID-19 pandemic and all. It was nice knowing that even if just a little bit, my research could help someone save a life.
Excellent, excellent. So we'll give one more question. Were there Python packages for the filters you used, or did you build them all on your own?
Oh yeah, I forgot to mention that actually. I designed the simple moving average filter by myself. Three of them, I believe the median, the Savitsky Golov, and the Weiner, were all pulled from SciPy's signal processing module. And the exponentially weighted moving average filter, I believe, is simply a function in pandas, if I'm correct. But for the rest of the answer, no, I did not design most of those myself. They were pulled from modules and libraries elsewhere.
All right. Well, Jackson, I want to thank you again for participating in piPACT, for your excellent work and excellent presentation. And I'm sure, like you said, research is always exciting. So I hope you continue to find that to be the case moving forward. So with that, we will move on to our next presenter, Joseph Rosenfeld, whose title of his work is Lowering Total Scan Times to Conserve Power Usage for Bluetooth Proximity Detection. I want to make a special thanks to Joseph. He was very proactive on the Piazza. I'm sure a lot of if there are piPACT participants present, they'll recognize Joseph being one of the more prolific respondees on Piazza. So much thanks to him for being such a good community member. So Joseph, if you're ready with your slides and your audio, the floor is yours for the next 10 minutes.
Okay, so hello everybody. I am Joseph Pinchas Rosenfeld, and this is my project, Lowering Total Scan Times to Conserve Power Usage for Bluetooth Proximity Detection. So a joke I heard goes, an ICU doctor, an epidemiologist, and a virologist walk into a bar. Just kidding, they know not to do that. However, the average person might not, and if they have COVID, then they might infect others who will spread it. Therefore, it's important to have automated contact tracing, which is privacy preserving and helps people know if they have been in close contact with people. The goal of the PACT project is to use Bluetooth and phones to do this, and to be able to tell if the people were really within proximity or not. The thing is, Bluetooth uses battery power. People won't want the app if it uses a lot of their battery life. people always want more battery life out of their phones, and if this app takes a noticeable amount of their battery, users will not want the app. They might uninstall the app, not run the app, not allow the app to share their data, and they will most likely also complain about the app. This would not allow for Bluetooth-based contact tracing to be brought to its full potential. So we want to use less Bluetooth so we can scan less. But if we scan less, we get more noise in our data. The question becomes how will more noise and fewer data points affect the accuracy of a proximity detection algorithm? I tested if lowering the number of scans can be used to save power while keeping precision for proximity detection. Saving power is important, but so is being accurate in detecting if people are actually within proximity. Overall, I collected two main data sets. The first was a more ideal data set for the conditions between the two Raspberry Pis. There were no obstructions in between the devices, and the devices were at equal heights. However, this is not what smartphones will experience in everyday usage, and this project hopes to use Bluetooth proximity detection in smartphones. Therefore, I made a second data set in which I changed the heights, obstructions, and orientations, and put the Raspberry Pis under many conditions that a smartphone is more likely to experience in real day-to-day life. I called this my realistic data set. For each data set, I collected measurements with the devices within proximity and not within proximity. In this context, I declared within proximity to be 6 feet or less and not within proximity to be greater than 6 feet. For the first data set, I collected measurements with the devices, For the first ideal data set, I used many different total scan times and intervals within those times to actually scan. However, it became clear quickly that the total number of scans is really what mattered. So, to simplify, for the second realistic data set, I always just set the interval between the scans to 1 and just adjusted the total amount of time and therefore the total number of scans. So I used two algorithms for doing proximity detection so that I could see in general if algorithms can be accurate when using fewer scans, and so that my conclusion was just not saying that one specific algorithm can be used reliably even without very many scans. So the first algorithm that I used was one in which you can take the average of the data values and you compare it to a preset value to determine proximity or not. In further reference, I will call this the average technique. The second algorithm, which I called the M of n technique, was when you count the number of values that are all of a certain preset threshold, and if the number of those values is great enough compared to the total, then you say that devices are within proximity. For example, if half of them are greater than -60, then they're within proximity. My goal for these tests was also just to say whether or not the devices were too close or not too close. My goal was not to determine the exact distances. Also, for each algorithm, to optimize them, I set up graphs to determine the optimal values for the preset thresholds. When looking at accuracy of algorithms, I looked at 3 different statistics that helped tell me how accurate the algorithm is, as there are many different aspects to look at when determining the accuracy of an algorithm. So the first one is precision, so true positives over true positives plus false positives, and this shows how many of the scans that were marked to be within proximity were actually within proximity. The next one is sensitivity, so true positives over true positives plus false negatives, and this shows how many of the scans that should have been marked positive were actually marked positive. Finally, we have specificity, which is true negatives over true negatives plus false positives, and this shows how many of the values marked false to be not within proximity were truly marked to be not within proximity. So here I have 2 graphs of how the number of scans affected the number of correctly marked sets from the total when using the average technique, with the ideal data set on the left and the realistic data set on the right. We can see for the ideal data set that it begins to fully plateau at about 7, shown by the black arrow, and fully plateaus at 15, shown by the blue arrow. Therefore, in my comparisons, I compared accuracy at 7 scans versus 15 scans. However, when looking at the realistic data set on the right-hand side, we see that although at about 15 there is no gain really going higher, there is still some gain on the line titled near after 7. The real question becomes, how much gain is that, and how does that affect the overall accuracy? So here I present to you a table of my overall findings. On the top you have each algorithm, and on the left you have both data sets for both 7 and 15 scans. We can see that for both algorithms under the ideal data, there were very small, if any, changes between the overall accuracy at 7 and 15 scans. The EMMA event technique had no changes whatsoever, while the average technique lost about 1% for precision and specificity. Looking at the more realistic data set, we see very small changes in precision and specificity between 7 and 15 scans. However, we also do see slightly higher changes in sensitivity. However, in the big picture, these changes are still not very big, and when implemented, the decision will need to be made about whether these small gains are worth the doubling the number of scans and therefore battery power usage. Therefore, I came to the conclusion that Bluetooth-based proximity detection can be done without very many scans. All of this work was done for lowering scan times, but none of it will work very well if there is not an advertiser to scan for. Advertising continuously would also take a significant amount of battery life and is not ideal. However, scanners need to hear the advertisers and are less likely to do so if the advertiser is not advertising very frequently. To solve this, we can take advantage of the connected and very accurate clocks built into smartphones and internet-connected devices, and to set up that the advertiser and the scanner operate at precisely the same time at a specific interval, such as exactly on the 5s. If everything is being bunched up like that, then it makes a lot more sense to have a short interval, which is another reason why I chose to have the set of interval of 1 in my tests. Early tests of this method have been successful. However, I would need to test it more and try it with smartphones to actually declare it successful. Also, when looking back at the previous table, the numbers for the realistic data set were not very accurate nor ideal for Bluetooth proximity detection. Different or more sensors might need to be developed, and better algorithms also should be developed, and when they do, they should take into account how many scans are necessary for them to operate properly in order to maintain low power usage. Lastly, as everyone here will say, this all was done with Raspberry Pis, and these ideas and techniques will need to be brought to smartphones. With that, I'd like to end by thanking everybody for listening to me today, and especially thank the entire piPACT team for facilitating an independent project. I had a lot of fun and learned a lot from it, and I guess I can take questions.
All right, thank you, Joseph. Excellent presentation, reflective of quality work. So let me just review what questions there may be. So I'm going to start us off with a question. So you created two different data sets, one that was ideal, one that was realistic. Along those lines, do you think there's merit in sort of adaptively changing the scanning or advertising intervals based on, an indication of the environment you're in, or something like the metadata that you're indoors versus outdoors? Do you think there's merit in such a concept?
Yeah, I think so, because if you know that you have a set parameters, you could probably scan even less, but I didn't really investigate that much.
Okay. All right. We've got some questions coming in. First question, were you able to obtain specific data for power usage of the Pis?
No.
Any additional detail you want to provide on that, or just?
I'd assumed it just wasn't a lot measurable for the Raspberry Pi itself, but in smartphones over time, it does take battery life out of it.
Understood. All right. Did you include measurements with the human body in close proximity to one or both Pis?
It was just one. Sorry if that was not clear.
One. If you did put a human in there, did you vary the geometry during the measurement time?
What do you mean? I'm sorry, I don't really understand the question.
Okay, so we'll let the person who's asking that clarify for themselves, but I'll give you my interpretation. Did you, for example, vary whether if there was a person in between the two Pis, were the sort of the broad or the wide part of them facing the Pis, or was it the more narrow aspect?
It was everything in between and both sides, yes.
Okay, so you did sort of all
I did all the kind of things that I thought smartphones would be likely to experience and then would see in their measurements.
All right. We'll let whoever asked that edit or follow up with that if they so choose. I'll add some words to this next question, and then we'll see if there's any more after that. So did you consider any other analysis algorithms where I'm going to interpret analysis algorithms as other things than M of N or other such techniques?
Yeah, I did, but these two seems the most likely to behave properly with less data, and looks like, and in when just initially testing with the ideal data set, we're getting the best results anyway.
Gotcha. All right. And then we have a comment from one person saying that Boeing has found that sacks of potatoes behave like a human body as far as affecting radio waves. I've seen that. I've seen that before. I've had varying personal success with that, but excellent. Well, so just to try to keep us on, I think, on schedule, we're going to, first of all, thanks Joseph again for taking the time not only to contribute to piPACT and participate, but again, for being such a proactive member in the course via Piazza and sharing his work with us. And we hope to hear from you soon in other venues and to have continued success.
Thank you.
All right. So with that, we'll go on to our fourth presenter, who is Nadine Han. I hope I'm saying that correctly. God knows I know the pain of having a name that's often mispronounced. But
Nadine, you got it right.
All right, great. I feel good now. I can end on a high note. Nadine's work is titled "Determining Certainty of RSSI to Distance Conversion Through M of N Processing and Understanding the Effects of Various Environments." And I must say, you're well on your way to writing technical papers, because a conference paper without at least 20 words in the title is no conference paper at all. But that's excellent. So with that, Nadine, if you're ready with your slides and your audio, the floor is yours.
My name is Nadine, and my project is, again, determining certainty of RSSI to distance conversion through M of N processing, which Joseph did touch upon in his presentation, and understanding the effects of various environments. I'm from Boston, Massachusetts.
Apologies to everybody for the technical difficulties. Brave new world we're in. Are we good?
Awesome.
Barry, full screen and all?
Looking good.
All right. All right, Nadine, let me go the first slide. There you go.
Yes, no problem. Sorry about that. Okay, so the overall goal of my project was to determine distances of Bluetooth Low Energy or BLE advertising devices. So these are things like phones, wireless earbuds, Fitbits, any personal device from a scanner, which is the device that measures the BLE signals, based on the received signal strength indicators or RSSI measurements that the scanner takes. So the way I did this was by focusing on two specific areas. The first area is how certain factors other than distance may affect RSSI. So in this project, it was orientation and height of the BLE device, indoor or outdoor measurements, and line of sight obstructions. The second area of focus was how to determine if a scanner's distance to a BLE advertiser is too close, or within 6 feet according to the World Health Organization, with an acceptable level of accuracy, or above 95%. So some general keynotes about this project. First, that I used 2 Raspberry Pis as the primary BLE advertiser and scanner. These were provided to every piPACT participant. And for this advertiser and the scanner, I leveraged the Python GATLib module. So I used those functions to run the advertising and scanning so that it could pick up all different types of BLE devices, not just the other Raspberry Pi. For these specific devices, I also wired them to external breadboards just for better control. I'll explain more about that in my experiment slide. Another keynote is that these measurements were taken at half-second intervals for 10 to 30-second durations. So that's just how the data was collected. And most importantly, I focused on near and medium distances, which I defined as 1 to 14 feet. And the reason why is if we have a defined threshold of 6 feet, it's actually a lot easier to determine if the RSSI is a value is measured outside or inside this range, the farther away it gets from the threshold. But the problem is, once you get closer to that threshold, the RSSI measurements tend to get muddled because of different ambiguities in the environment, like the factors that I was studying in this project. So if you can move to the experiment slide, that'd be great. So for this experiment, the main materials I used for the advertisers were a Raspberry Pi 4 and an iPhone 8, for the BLE scanner, it was a Raspberry Pi 4. So if you take a look at the image at the very left, you can see the setup for the scanner. And the way I wired it was I just connected this Raspberry Pi to two different LED lights. One just indicated the overall power, and then the other one indicated whether it was scanning or not. So the reason why I did this was to just allow for me to take data outside without having to be connected to Wi-Fi or having to be connected to a monitor. So it just made things a lot easier. The middle picture shows all the advertisers. So there's the iPhone 8, which had to use an NRF Connect app in order to advertise. And then another Raspberry Pi 4, which is basically configured the same way, except it's running an advertising function instead of a scanning function. And then the image on the very right is the overall test setup. So the scanner was connected to the advertiser by a 14-foot long string. The advertiser was propped up on a tripod that was at 1 meter. And basically like that specific height was just determined by sort of like the midriff of the person holding the scanner, which in this case was me. So the purpose of the string was to just allow for easier distance keeping because the string was exactly 14 feet. It also allowed me to move at different angles while keeping the same distance. And the string also had separate markings for every 1 foot, so that way I could change the distance if I wanted to. So the main factors considered in this experiment, in my experiments were A, the distance between the advertiser and the scanner, which ranged from 1 to 14 feet. B, line of sight obstruction. So basically any objects that would have been like between the scanner and the advertiser. In this case, only one was tested. It was one person. I just chose the most extreme case because oftentimes like things like having like a cloth covering your phone is a lot less obstructive than having an entire human being. So in this case, one person was just used as the obstruction. It was also the person holding the scanner. Another factor considered were indoors versus outdoors. So like how confined the space the advertisers and the scanners were in. And then there's also advertiser orientation. So at like which angle the measurements were taken of the advertiser. And then finally, the scanner height above the ground. So that's 0.1 meters, which is about foot level. There's 1 meter, which is about middle level, and then 1.5 meters, which is about head level. So if you can move on to the data analysis. Great, awesome. So after taking all these measurements, I decided to plot them out to see how the RSSI distribution went. So if you note in the first graph at the top on the very left, there's the entire raw data distribution. I did omit orientation and height because I decided to isolate for distance being inside, outside, and unblocked and blocked just for this specific data analysis, but I will address it in the next slide. So if you take a look here, you can note that the RSSI distribution is following a certain trend. So the closer the measurements are taken to the scanner, the higher the RSSI tends to get. But there's also a really big variation in the RSSI measurements, and that's because of all the ambiguities in the environment. So the next step I thought was how many points do I need to be measured at one place in order to say with some level of certainty or a high enough level of accuracy that an RSSI value was measured either within 6 feet or outside 6 feet. So that's where the M of N processing came in. So if you look at the middle graph on the top, what I did was I tested 9 different cases or scenarios, and each case just consisted of combinations of indoor, outdoor, unblocked, blocked, and different advertiser data. And they, like each case determined the train and the test data sets. So what I did was for each case, I split the data into far measurements and close measurements, and I plotted it on that probability distribution function right there. So I applied a Bayesian algorithm to get a starting threshold, which is kind of just like the overlap between those two distributions right there. And if you notice, like the thing is, even though there is a threshold, there's a lot of overlap, like especially around the middle. And the thing is, the threshold like hard identifies anything to the right as close and hard identifies anything to the left as far. And although this may seem like it's not accounting for things like overlap, you have to remember that like in the real world, we won't actually know if the RSSI measurements are truly far or truly close. There's no actual truth when we're applying this in the real world. So because of that, the best thing we can do is try to find a threshold that minimizes false negatives and positives while also maximizing true negatives and true positives. Just for a note, false negatives and positives means like incorrect identifications. True negatives and positives means correct identifications. So during the testing process, so actually using this threshold, I used M of N processing to predict which group the testing data fell within and use the truths of the testing data to compare to the predictions to make a confusion matrix. So that's the little graph there on the very right at the top. Just as a note, the way I define M of N processing is just taking endpoints ranging from 1 to 7 in this case, taken at the same distance from the testing data. And if at least m out of n points, or the majority, fell within the near group, that overall group of measurements was categorized as being taken in a near distance. So after getting a confusion matrix, I shifted around the threshold experimentally to minimize the difference between the false negatives and the positives for that specific m of n pair. So each m of n pair got its own confusion matrix. That's how I compared which one was the best. So the way I kind of chose the best pair was I just chose whichever confusion matrix had the smallest difference between the false positives and the false negatives. But obviously there were some confusion matrices that were pretty similar. So what I did for that was I just chose whichever one had the highest true positives. But then if there were also ones that had similar highest true positives and similar differences, then I would choose the one that had the smallest number of points, because the faster we can identify if something is near or far, the better it is. So from there, after taking these best m of n matrices, I then compared the cases to each other. So if you look at the left graph on the bottom, there's a plot of some of the examples, cases 1 through 4. And case 4 was actually the ideal classifier in this case. So what case 4 did is just return a 75% true positive rate at 80% accuracy, which it was also a 4 out of 7 classifier. But the problem here is, remember, we want a 95% accuracy, right? So this falls underneath that by 15%. And that means that it's not necessarily the most ideal classifier in this situation. If you look at this graph of an optimized classifier performance, I graphed out the ideal classifier versus this case 4, the best classifier I actually got from the data. And you can notice how it falls pretty short of that. If you can move to the next slide, that'd be great. But then there's actually another layer of complexity onto this classifier that can also decrease its accuracy, and that's orientation and height. So on the left, I basically just showed how orientation and height can affect an RPI advertiser when the advertiser is at height 1 meter, it's outdoors, a fixed distance of 6 feet. So if you take a look at the graph, you can notice that a different orientation or height above the ground can result in a variation in RSSI values taken by the RPI by 4 dB. And this is probably caused by things like antenna radiation patterns and ground reflection. But another really interesting thing here is when I swapped out the RPI for an iPhone advertiser, I noticed that the orientation had a way less significant effect on the measurements. So it was, rather than being 4 dB, it was less than 1 dB. So obviously there's a very big discrepancy between advertisers, and orientation and height has some kind of effect. If you can move on to the last slide. Great. So the main conclusion from here is that the best classifier I could achieve with this data was a 4 out of 7 classifier with a 75% true positive rate and 80% accuracy. But then another thing I noted is that different advertiser orientation and height can introduce variations in the RSSI, and that also varies depending on if it's an RPI or an iPhone. And then the biggest takeaway from here is essentially that a more sophisticated algorithm than M of n should be used in order to improve accuracy to be above 95%, which is the ideal accuracy in order to deem this kind of thing feasible for contact tracing. So some next steps would just be to test other advertisers to find ways to account for the discrepancies between them, and also to look into other types of obstructions, because obviously those will always affect the classifier accuracy as well. So with that, I'm open to any questions.
Excellent. Thank you, Nadine, for a very excellent presentation and very interesting work. So let me just, I'm going to stop the share here so I can go check out the questions. All right, we got some good questions here. So first question. So here's just a functional question, a really easy softball. What program did you use to make the graphs?
Oh yeah, of course. I use Mathematica. Yeah.
If you had considered the scan time as another parameter, do you think the far and close histograms would separate out?
I definitely think so. Yeah. So the thing is, part of the reason why I feel another step, I think there's a lot of more research that can also go into the M of n identifier, is because the data set I had, I think, was pretty small in comparison to what I would have liked to have, because I only took 10 to 30 second measurements. So the data set honestly was pretty small. I think had I taken a lot longer in order to take these measurements and scan for longer, the distributions probably would have become a little more distinct and would have made for an easier or a higher classification rate for sure. I think the longer you spend getting more points, the more likely you are to identify something. But it's also kind of you have to find that balance, because you don't want to spend 3 minutes and then say oh yeah, now I was too close to that person. But you kind of want to identify as quickly as possible with a high enough accuracy that you are maybe within proximity of that person for too long.
Nadine, do you think there's value in developing separate classifiers for different scenarios or different configurations?
So
For example, indoors versus outdoors.
Yeah, so I actually also thought about this a lot. The reason why I actually tested certain cases where I just bunched stuff together is because the way I like approached this, at least, was that I believe that like we wouldn't know any of the environmental conditions of the scanner or the advertiser, because I think part of the reason why we're doing this type of contact tracing anyways is because of like things like privacy concerns. Like people don't want like other people to know like they were in this place at this time. So because of that, like even though if we can have really great configurations that can be really accurate, we won't be able to apply them when we take actual measurements because we don't know if the scanner was indoors or outdoors. So I think it's possible to make it. I'm just not super sure how that would transfer over to real life, if that makes sense.
Yep, no, absolutely, absolutely. And it's very encouraging that you remember the P in PACT. You mentioned more complex or more sophisticated algorithms than M of N may be needed to improve the accuracy to the desired level. Do you have any ideas on what those algorithms might be?
So this is a really great question. I actually I didn't start off thinking about M of N when I first did this project. If anything, like the way I wanted to approach it was sort of like a brute force method. So I was like, okay, so taking 1 point clearly isn't indicative of like for sure we're within this distance or not. So like how many points do I need? So then I was like, I have to figure out a method to just test like 1 point, 2 points, 3 points, 4 points, 5 points, like along those lines. So then M of N fit that the best. So I'm not super well researched on like all other types of techniques. I definitely think there are algorithms out there that are probably way more complex and like probably account for a lot of other things. But M of N was really the only one I looked into because it fit my approach.
Excellent. Well, thank you for the very detailed answer. So with that, I again like to thank Nadine for sharing her work. Excellent presentation, and for obviously thank not only our presenters but all the participants of piPACT for contributing to what is undoubtedly going to be a critical tool, critical quote-unquote weapon in our fight against infectious diseases going forward and currently. You know, I want to emphasize to all the audience that this is an actively researched problem. You know, while we've challenged our students to explore this area, it does not mean it's solved, right? It's not been solved by folks at MIT, at Lincoln, whatnot yet. So it would be naive of us to expect the solution to come out in a course of 6 weeks. But we do recognize that the work that these students have done will undoubtedly contribute to the larger understanding needed to make it a viable solution. So with that said, I invite everybody to return in due time at their leisure to the Beaver Works Summer Institute main stage, where the sort of final closing event will be going on. And if you have any desire to learn more about piPACT or whatnot, please visit the BWSI website and contact us at the contact details provided.